For years, scientists have disagreed on how fast the universe is expanding. Some say it's moving at one speed, others say it's faster. The gap between their answers hasn't gone away. But what if this cosmic disagreement isn't a sign of new physics, but just a sign of old mistakes? Welcome to Metalog, the show where we turn cutting-edge science papers into stories you actually want to hear. I'm your host, and today we're diving into a study that might help settle one of the biggest arguments in modern cosmology. How fast is the universe expanding? It's called the Hubble constant, and a new study suggests we might be closer to the truth than we thought. The Hubble constant is a number that tells us how fast the universe is stretching out in every direction. It helps us figure out the age of the universe, how far away distant galaxies are, and even what the future of everything might look like. There are two main ways scientists try to measure it. One method looks far back in time, using leftover light from the Big Bang, what's called the cosmic microwave background. This is the early universe method, used by telescopes like Planck. The other method looks at nearby galaxies. It uses special stars and exploding supernovae to measure distances in the modern universe. Here's the problem: those two methods give us different answers. Imagine two radar guns aimed at the same car. One says the car is going 67 kilometers per second per megaparsec. The other says 73. That's a pretty big difference when you're talking about the speed of the entire universe. Scientists have been calling this the Hubble tension. Some think it means we've misunderstood something deep about how the universe works. Others believe we just haven't measured things carefully enough. And that's where this new study comes in, with a third way to get the answer. Wendy Freedman and her team at the Chicago Carnegie Hubble program wanted to avoid the usual problems that come with measuring certain stars. So instead of using Cepheid variable stars, the common choice, they used two other types of stars. First, stars at the tip of the red giant branch. These are old stars that stop getting brighter at a very specific point, kind of like a dimmer switch hitting its limit. Second, carbon-rich stars in a phase called the asymptotic giant branch, also known as JAGB stars. These stars shine very consistently in the infrared, and they're even brighter than the first kind. What's great about both types? They tend to live in less crowded, dusty parts of galaxies. That makes them easier to measure with precision. The team used the James Webb Space Telescope, which sees in infrared and has incredibly sharp vision, to study 10 nearby galaxies that had each hosted a Type 1a supernova. These supernovae act like mile markers, helping astronomers stretch their distance measurements farther into space. And to make sure everything was on solid ground, they calibrated the whole system using a galaxy called NGC 4258. That galaxy's distance has been measured with lasers made by water molecules, natural lasers in space called masers. It's one of the most accurate distance markers we have. Here's what they found. Using only the red giant branch stars with James Webb, they got a value of about 68.8 kilometers per second per megaparsec. Using the carbon-rich JAGB stars, they got a similar number, about 67.8. When they combined both methods, the result came out to around 69. Then they added in extra data from the Hubble Space Telescope, and their final best estimate was about 70.4, with a small margin of error. That's right between the early universe and late universe estimates. In other words, it doesn't take sides, it finds a middle ground. This result is important because it suggests that the disagreement between measurements might not be about the universe breaking the rules. It might just be that we were looking in the wrong places or relying too much on stars that are hard to measure accurately. The tip of the red giant branch and JAGB stars offer a cleaner, more stable way to measure distances, and the James Webb Telescope gives us the clarity we need to use them well. This study doesn't prove either side of the debate was wrong, but it suggests the fight may not have been necessary in the first place. There's a catch. Even in the best studies, a few supernovae carry most of the weight. In one earlier study, just 12 of 42 supernovae had such strong influence that if you tweaked one of them, the final number could shift by a full %. One example, called Supernova 2007 AF, was such an outlier that changing how it's handled moves the Hubble constant all on its own. So while this new method is promising, scientists say we still need more data, a lot more. The more nearby supernovae we can study with these new techniques, the more confident we'll be. The takeaway? We might not need new physics to explain the expansion of the universe. We might just need better tools, better stars, and better data. This new study gives us a fresh way to measure cosmic distances, one that lands right between the older estimates and helps ease the tension. But we're not done. Upcoming telescopes like the Nancy Grace Roman Space Telescope and the Rubin Observatory will let us test these findings with much larger samples. We'll also have new tools like gravitational wave sirens and lensed supernovae to cross-check everything. The future of measuring the universe looks brighter and clearer than ever. So, do you think the Hubble tension is finally on its way out? Or is the universe still holding on to some secrets? Let us know what you think in the comments. And if you enjoyed this breakdown, hit like, subscribe, and share it with someone who loves science as much as you do. Until next time, stay curious and keep looking up.